So in the last class we were here, right? I think we discussed this slide. I think I repeat so that continuation will be perfect. So after understanding the harmonic oscillator quantum mechanically, its solutions and eigenenergy. Now, as I promised that we can show that the electromagnetic wave, a mode of electromagnetic wave, can be considered as a quantum harmonic oscillator. So how that is that we want to show now, and then we can proceed for actual quantum photonics related stuffs. So you know all that from the Maxwell's equation, we can have this energy density. Energy density is half of E dot D and H dot P. So this is related to the energy associated with the electric field. We said that that is like a half epsilon E square, meaning your energy stored like a capacity property of the medium. It can be free space, then it is epsilon 0. And this one is like a half mu h square. That means it is something like that magnetic energy stored in an inductor like property of a medium or free space mu 0. That is known, that we have derived earlier. And from here actually we can just instead of 4 different variable, we know their relationship E and D and H and B, so we write like this. In terms of E and B we are writing. Why B? It will be clear a little while later. You know, this is energy, and we know we have started our harmonic oscillator also. If you see, we have started with a Hamiltonian. Hamiltonian means total energy, kinetic energy plus potential energy. And for electromagnetic wave, energy means this, electric field energy and magnetic field energy. Energy associated with the electric field, energy associated with the magnetic field. So here also we are considering also energy, density. Instead of total energy, we are considering energy density. That means at a particular position R and instant of time T, we can have, you can consider a unit volume. And within that unit volume, that can be per meter cube, per centimeter cube, depending on the unit of electric field and magnetic field, how you are expressing. Right? So this is per unit volume. Only this much the difference. We are not considering total energy of the entire electromagnetic field spreaded over the space. We are just considering just energy density. So to proceed with this, because you know that in terms of, in case of our harmonic oscillator, the Hamiltonian is expressed in terms of momentum and position. And momentum, again, you know that momentum is nothing but m dx by dt. So ultimately that is the position time dependent variations. That is what you can express the total energy of a harmonic oscillator. Here also, if we can find like a particular variable similar to what is expressed for simple harmonic oscillator X, that would be great. We have all the tools in our hand. We just need to little bit manipulate, because in electromagnetic field, we know that for certain explanation, we introduce a kind of vector potential. Vector potential, and another one is scalar potential. Scalar potential, you know, phi. That means what is the potential at every point because of some charge or because of some electric field, whatever there, we can express potential. We know that typically the potential is equal to negative gradient of the electric field is that equal to negative gradient of the potential, or normally you know equal to minus dV dx. In semiconductor normally we use that, equal to minus dV dx. There V equal to the potential of difference between 2 points separated by dx. So in 3 dimension, we just say instead of V we are writing phi here. So E minus d phi, that is normally we know for any electric field, Any circuit analysis, any device analysis, normally we semiconductor device analysis, we use this thing frequently, electrostatic solutions. However, similar to scalar potential, which is related to electric field, we can also define vector potential. Sometimes it is called magnetic vector potential, because you know electric field can be generated out of time varying magnetic field. That is what we know, that time varying magnetic field that is actually can generate electric field, and time varying your electric field can generate magnetic field also. That is what electromagnetic theory is. So we express this one, that is famously called as a Coulomb gauge. Right? Coulomb gauge is just minus delta pi and del A del T. We are writing, expressing that one. We are adding certain things. We are adding this thing does not mean that is for nothing. What we say that since it is A is the vector potential similar to electric field, okay, the vector potential is expressed such that it is giving B once you get a rotation. Curl of A should give your magnetic field. Okay, meaning if you know magnetic field, you can find out what could be the vector potential. And if it is vector potential, if you just put down here, I think for time varying case, it is perfect. Okay. Now, let us, for simplification, we consider that free space. Okay. Where you don't have any charge at all, or homogeneous medium, charge-free homogeneous medium. Homogeneous in the sense, dielectric constant is uniform, not direction dependent, and magnetic field as well. So if we just consider that type of situation, we have the liberty to consider delta phi equal to 0. That means it's an equipotential everywhere. No potential difference is there. It's kind of free space, charge free is there, so should not be any potential difference. So in that case, we can simplify this Coulomb gauge just by putting delta phi equal to 0 for special situations. Uniform situation, you need not to, but that will create complicacy. But our target is to show how electromagnetic wave is can be expressed like a quantum harmonic oscillator. So now you see, again we know that Gauss theorem, Gauss divergence law, divergence d equal to 0, because if there is a charge, we would write rho here, divergence d equal to rho, because charge free we can write divergence d equal to 0, and it is homogeneous, so epsilon can be taken out. That is not a function of x and y and x, y, z, position dependent. So epsilon taken out, that means divergence equal to 0. Now you just try to see divergence E equal to 0 here in equation 214. So what you get, ultimately we can get safely say, once it is say divergence equal to 0, here equal to del T, divergence E, that is equal to 0, and this one is 0, and del T we can write a divergence A. Normally E can be 0 when divergence A is constant, right? Divergence A is constant over time, then del T will be equal to 0. But for simplification, anything constant we can set it to 0. So we can safely assume that divergence A, instead of considering constant, we can consider some number, some 0 we are putting, so that our life will be easier. Okay. It can be different, but that will complicate our situation to interpret directly with the quantum harmonic oscillator. So it is safe to say that. So now what we do, you know, this A is related to magnetic field. You know, magnetic field and electric field we can express in free space like a plane wave, right? And if it is a different k value is there, wave vector is there, we can just integrate over that. So since B is like a plane wave, curl of A will be also can be expressed in terms of plane waves. So we express this ART, position dependent vector potential, um, uh, by its Fourier components. So that means I can say that AKT is like a weightage of A for a given K wave vector and plane wave. Time dependent term will be associated here. Anything time dependent, I'm just associating with including this one. Normally it is a plane wave, it is I omega t if it is single frequency. But that time dependent part I am just enclosing here. And normally, you know, Fourier expansion 1 over 2 pi square root, but if it is 3-dimensional, that is how it is a normalization. It does not matter much for our explanation. So this is something coming from the normalization or simplicity, right? So far up to this point, it is clear. So I have just introduced vector potential. Apart from that, everything we know, okay? And that vector potential we are expressing such that it is actually satisfying Maxwell's equation in this form. So some kind of, it is, you know, just to explain something, you introduce something. For example, while propagation of electromagnetic wave in free space, you have to consider some kind of constant like mu0 epsilon 0. Similar type of thing. Then only it satisfy our practical experimental results. So here also we have introduced A. As of now, you can just consider like that. Okay. Now you see, you just consider this ART, whatever you get, and put down in this equation, curl of A. So if I just put down this equation ART here, what you get? That means you are, this is del means you just normal way you can just do curl of A. You can consider only 1k. Instead of integration of this thing, you are considering just 1k you consider and put down here. Then that means one wave vector, one particular direction, one wave vector, one frequency is somewhat you can decide. Then what you get ultimately from Maxwell's equation also you have seen anything curl of electric field or curl of magnetic field is there. Once you take curl, that means it can be expressed, and this is a plane wave, only ik. This del operator gives you ik. That you can check with a simple vector algebra. Okay, that will be ik. So if I just put AR here and then operate with a curl, then what we get as a eigenvalue, you will be getting ik cross akr, akt. Okay, because time dependent function we have used there. In this equation, we have used time dependent akt. You are using this thing as a whole. So, and also if you just consider, we have considered divergence A equal to 0, that also gives you operator ik dot 0. So this thing ensures that for this spatial consideration, okay, it need not be, some other situation can happen. For this spatial consideration, we can directly say that A is perpendicular to K. That means K is a vector, A is a vector, cos 90. So that means cos 90 means 90 degrees. So A is just perpendicular to K. And here we see that B also perpendicular to both A and K. So what does it mean? A is in the direction of, for this special case, it is in the, you can consider this is in the direction of electric field. Okay, because you know B is normally perpendicular to K and E. K cross E equal to B or H we normally know. So in this particular situation, we can assume that A is particularly along the direction of electric field. But you should remember that if you are getting some constant here that may not be perpendicular to along the direction of electric field, that thing you can keep in mind. Okay, for this spatial situation, what we get, A is perpendicular to K, and hence BKT here. So perpendicular to K means this is your sine 90. Sine 90 means 1. So B I can write directly IK AKT. So the mode of this thing we can just write down like this. Okay, though B is a perpendicular to A, that's why I have not simply written B equal to AKT. So this is a mode of something like that. Their directions are different actually, of course. Only their mode, their length actually is related like this. The complex things are there. A can be also complex. Okay, so that's why you are taking mode, but it is like this. Now, from equation 214, 214 means this one. So I know this A, right? So I can write EKT, because A, if I express in terms of K and T, K is the wave vector, so EKT will be dAKT by dt. I am just considering instead of partial derivative, I am just considering, because once you consider one particular K, so I can just consider for that K value, I can just simple derivative. Okay. Now we have EKT equal to this one, and all these equation, what we do, the expression of E and B we have. Now B is this one and E is this one, 219 and 220. Expression of E and B. Where we put in the energy density. In equation 213 we have expressed earlier. E expression you put here and B expression put here in terms of AKT. Both E and B we have expressed in terms of vector potential. So we just put down here. We get equation 221. Okay. So what you get, epsilon 0 by 2 ddt of this one minus minus, it will become plus. Mode square, whatever complex value if it is coming after derivative, it's square, k square 2 mu 0 AKT. So simply 213, 1 by 2 mu 0, epsilon 0 half is there. This one is dA by dt, and this is whatever IKB AT. So simply we have written. Now you compare with the potential total energy of a harmonic oscillator of, that is actually quantum particle of mass m in a potential. Okay, parabolic potential. We know this is the expression, half mv square or p square by 2m, half m omega square. This is corresponding to your potential energy. This is kinetic energy. Now if you compare this 221 and 222, if you just assume this vector potential, whatever we are giving, that is equal to x, corresponding to position of a harmonic oscillator, x. And epsilon 0, you are considering m. That means half m, if this is x, dx by dt, half mv square. That means kinetic energy. So that means this term actually gives you p square by 2m. If you just consider epsilon 0 equal to m, equivalent to m, and mu 0 equal to 1 by mc square. This mu 0, if you just put mc square, and certainly once you consider this one, you know epsilon mu 0 equal to c square, so k square c square equal to omega square. You know omega by k equal to c, the phase velocity of a plane wave. K is the wave vector, omega by k equal to c. So once you consider epsilon 0 equal to m and mu 0 equivalent to 1 by mc square, then k square c square equal to omega square, then you just put down here, replace all this situation, then it is actually replicating your total energy of a harmonic oscillator. Now you see, whenever you are just assuming there is no mass, nothing. It is an electromagnetic wave, massless, nothing is there. But you can just imagine that any quantum particle of mass m, it is just disappear, m disappears, for example, and producing epsilon 0, and corresponding energy, you know, relativistic energy equal to mc square. You are just relating to mu 0, because once mass disappears, the energy will not disappear, of course, because they are relativistically mass and energy, they are related. So this thing actually in turn, it is converting into some kind of values, epsilon 0 or mu 0 of the medium. Then you get simple energy, but that energy will be just like a electromagnetic energy, and that is expressed here in terms of vector potential. Hopefully I could convey that the electromagnetic wave There are other methods also there if time comes, that if you are considering certain cavity also, there also you can show that this energy inside the cavity of when electromagnetic wave resonating inside a cavity, that resonance mode can be also considered, the energy of the resonance mode can be considered like a harmonic oscillator. But here we can show directly that any free-running electromagnetic wave in free space, it need not be a resonator, etc. And that electromagnetic wave, if you just consider a certain wave vector k is related to omega also. For that k, if it is propagating in any direction, any given direction, the energy density at every point, if it is free space, that actually directly related to your quantum harmonic oscillator. You can express. So once you express like this, you don't need to bother about m, you don't need to bother about your position, etc. You can directly relate it to your solution. You can imagine certain kind of eigenstate and eigenenergy of that mode. Okay, so that is actually since we have learned sufficient how to deal with a harmonic oscillator quantum mechanically, their solution, etc. So we can directly use this one, this equation 221, interpret this equation 221 quantum mechanically. Okay, so equation is similar, so solutions also quantum mechanically identical. So you don't need to bother about Hamiltonian. But what you can use your this creation and annihilation operator, raising operator and lowering operator, because that is good enough to understand a simple harmonic oscillator. We have shown that, right? So here is some conclusion. So the 5 points I just in a bullet form, you see. First point I'm just reading out so that it can be observed better. Thus we can interpret that each electromagnetic mode, each words you have to keep in mind what we are saying. If you a little bit change the wording, everything meaning will be different. We can interpret that each electromagnetic mode characterized by wave vector k, a certain wave vector you have to consider in a certain direction, and amplitude, we are considering amplitude AKT. Okay, that is a vector potential, we say, can have eigenstate solution psi n and energy eigenvalues En equal to n half h cut omega. So that is the thing. We can consider that this energy solutions, this energy, whatever total energy density, I mean to say, whatever energy density is there, corresponding to that, you can actually imagine a mathematical eigenstate solution psi n. Okay, and that eigenstate will have, of course, allowed energies En equal to n plus half h cut omega. So omega comes into picture there, because they are also omega related already. We have shown similar, k square c square equal to omega square. So omega term is there also. In this case, since k vector is fixed, omega is fixed. We are considering a particular mode, k is fixed, omega is fixed. Then the n represent the number of photons in the mode. So each of these photons will have energy of h cut omega. Just don't confuse with the quantum harmonic oscillator. That n changing means your psi n is changing. Psi 1, psi 2, psi 0, 2, psi 1, psi 2, psi 3 you can get, right? But in this case your each of this state psi n, you can have one particular eigenstate, you can have certain number of photons in that. All this quantum number, whatever the number coming here, that is corresponding to the number of photons in that kth mode. Because I cannot change omega, only I can change the n values. So they are called actually photons, whatever argued by your Einstein earlier. Okay. Now let us come back to the, because we want to consider photonics. Without laser we cannot deal with. Just simple electromagnetic things is not enough. Of course laser is a electromagnetic wave, no doubt about it, but it's a special characteristics is there. Laser is a special characteristics of electromagnetic wave, special engineered electromagnetic wave, specially engineered I would say. So we know that this bullet point 2, if you see, laser light emission is usually dominated by a single frequency, monochromatic. Of course, practically not, but we can say that almost monochromatic. Okay. So that means harmonic oscillator will have omega also. The laser emission can also be defined by a state function psi, laser emission. Now we don't want to recognize laser as an electromagnetic wave, EH, something like that. We can consider that laser emission for a particular frequency, monochromatic source, that can be stated as a state function psi quantum mechanically. Okay. Now we have the operator. We know that that operator we have defined in case of your normal simple harmonic oscillator, A dagger A in terms of position operator, momentum operator. In this case, we don't have position, momentum, mass. We cannot define like that. That is in terms of AM is there earlier when we find. But we can have different type of similar type, because it is also like a quantum harmonic oscillator. We can define this creation operator and annihilation operator also, but maybe a little bit different terms in terms of electric field, magnetic field. We will come to that point later. But obviously we can have that type of operator. Once we consider psi, we can define in the same fashion the creation operator or raising operator and lowering operator. So that means this one, this A dagger to state function psi, if you operate, suppose laser is emitting with a psi state. Now if you operate a creation operator there, then which describes a coherent laser light increases the energy by h cut omega. That means the laser emission is added. Suppose somehow you change the device operation such that one more photon is added. You can assume that that means one A dagger operator is operated on it. Creation operator. So one more photon is added. So number of photons increasing means, that means you can consider that this operation is happening. Creation operation is happening. Some operator is operating on this. And number 4, we may think of psi n as multi-particle state function. So normally quantum harmonic oscillator, whenever we are considering a single particle of mass m. But in this case, it is also simple harmonic oscillator, but n defines individually a quantum particle. So when we say psi n, that means it is a state function for representing n particle, n photons. We call that quantum particle for electromagnetic wave. Okay. Now, as we know, the requirement that whenever we are having A dagger, we can have A also, we can define. So that means, and also we can have a psi naught as well. Once n equal to 0, E0 equal to h cut omega, psi naught also there. Ground state solutions we have seen earlier. So here also we can have a ground state. That means that particular mode is not having any photon at all. So A psi naught, if you operate that one, that means you cannot really annihilate one photon from psi naught. That means that will give you 0. Describes the ground state. Oh, sorry, this is a typo. Ground state psi naught corresponds to the idea that vacuum contains no photon for the lowering operator A to annihilate a photon. A vacuum. That means when laser is not emitting anything. Okay. So that is a vacuum. So nothing is there. The ground state energy is the energy in the EM field before the laser has been turned on. So laser is completely idle. No bias, nothing is given, no pumping, nothing is given. But you can imagine that system still is having some kind of electromagnetic wave, electromagnetic mode, but energy is equivalent to h squared omega, which is called vacuum energy. Earlier we have introduced vacuum field energy, right? So now we come to this point. We understand the laser is nothing but we can consider as just creating and annihilating, particularly creating photons in number of photons, and that can be considered as eigenstate. And we consider monochromatic light waves. So that means in our hand, we are for the moment we are considering that electromagnetic wave for a particular mode k, the energy density in a certain point, energy density can be represented as a number of harmonic oscillator, and that harmonic oscillator solutions will be just energy quanta or quantum particle photons. Then in that light, if we try to understand this thing, that's a very simple example. I will give you task now. If you have a pen and paper in front of you, I ask you to calculate one important thing. Suppose you have a laser beam, somewhere source is here, emitting laser light. Okay, that means it is emitting photons. But classically we measure what? We measure what is the power of the laser. You know what is power, right? This power means we know from electromagnetic point of view, you have to find out what about the pointing energy, pointing from the pointing theorem, P equal to energy flow per unit area, half real part of E cross H star. That is that means energy flow per unit area per unit time, right? So that is the power. Suppose this laser is laser, you know, nowadays laser you can get some gigawatt, multi-gigawatt laser power can be there also, and laser can also emit as small as possible also. Small amount of light can be. We assume that this is emitting 1 nanowatt of power. Okay. So 1 nanowatt power it's emitting continuously. And you consider wavelength is 1550 communication wavelength. Right? And if it is emitting 1 nanowatt, I think I have written down some data here, some wrong data is there. I want you to confirm what would be the correct data it will be. Suppose it is streaming, power is going and streaming along this direction, positive x directions, you say. And let us consider 30 centimeter length of the path of the laser light, which is emitting 1 nanowatt power. Within 30 centimeter length, how many photons you can, is probable? How many photons you should expect? Anyone can calculate? I think I suggest you all try to calculate and let me answer. I'm giving you 2 minutes time. If you are just considering a 30 centimeter length of the beam propagating along x direction, emitting power 1 nanowatt only, how many photons you supposed to get? I think just take 1 minute time and calculate. It should not take more than 1 minute. Anyone? How you are approaching? Can you explain, anyone? What is your approach? Vaibhavi, you can explain? Yeah.
So, I thought maybe power into time would be nhc by lambda or something. So,
You know what is the photon energy? You can calculate, right?
yeah, that will be hc by lambda.
So have you calculated? I have written down 0.8 electron volt. Is that correct? If you just
I'm just doing it, yeah.
quickly, it should not take much time. This type of things frequently you have to encounter. Hc by lambda, just you have to put down. You know H value, I can tell you,
Yeah, yeah, yeah.
6.626 10 to the minus 34 joule second. Unit is important. Use that joule second and then how much you get. Are you getting 0.8 electron volt or anything else? Because we know that power is energy per unit time, right? Is that correct?
Yeah,
Energy flow per unit time is the power. Power into time is equal to energy. So,
n lambda into power by h into 30 centimeter.
yeah, right. So, are you getting 0.8 electron volt? Is that correct?
Separately, I haven't done, like I did it in SI units and that also. I'm
SI,
just calculating it.
SI unit, you will be getting joule, right?
Yeah, yeah, I'm just doing it.
Hmm. Animesh, are you trying? Hello, Animesh.
Yes, sir. Yes, sir.
Trying, yeah?
Yeah.
Tell. Okay.
Sir, it is nearly equal 10 to the power 22
10 to the power 22 what? Which one?
number of photons.
Oh, really? That's somewhere you are doing mistake. In 30 centimeter length, right? 30 centimeter, then I put 1 nanosecond, you know,
Oh, okay, okay,
because
sir.
if you
Yes.
take the velocity of light, 30 centimeter length traveling time is 1 nanosecond. 3 into 10 to the power 8 meter per second, no?
Yes, sir.
So 3 into 10 to the power 8 meter means 3 into 10 to the power 10 centimeter per second. So 30 centimeter corresponding to 1 nanosecond time of travel, time of flight. So that means if you expose your photodetector for 1 nanosecond in the path of your laser light, right? How many photons you should detect within 1 nanosecond? That will be the number of photons content in 30 centimeter length. That way you think. So number of photons contained in 30 centimeter length is equivalent to the count of photons in your photodetector in 1 nanosecond duration. If you are just putting your photodetector in front of your laser and you wait for 1 nanosecond and then see what is the number, that will be your count. That will be your number of photons content in 30 centimeter long beam, laser beam. I need to know at least how many photons are passing per second, then 1 nanosecond you can calculate number of photons. You know what is the power passing, energy passing per unit time? 1 nanowatt means what? 1 nanojoule per second. Is that correct? 1 nanowatt power means 1 nanojoule per second.
Per second, yes.
Yes. Now you know that much energy is passing per second. And you know the photon energy. So if you that 1 nanojoule you divide it by photon energy, then number of photons you will be seeing per second, right? And if that is the number per second, I want how many number of photons you would see in 1 nanosecond. So you have 1 nanojoule divided by 0.8 multiplied by 1.6 into 10 to the minus 19. You see 0.8 electron volt means 1 electron volt is 1.9, sorry, 1.9, 1.6 into 10 to the power minus 19 joule. 1 electron volt is 1.6 into 10 to the minus 19 joule, right? So 0.8 into 1.6 into 10 to the minus 19 joule. That is the energy of a photon. And you divide, you take inverse of it, then you get the, that means 1 nanojoule per second means that is the number of photons per traveling per unit time. How many, what is the number of photons passing, crossing at any point per unit time, per second? That number you tell me first. Murali Krishnan.
Yes, sir. Sir, I calculated number of average photons. It came up to 7.8.
7.8. Okay, anyone is getting beyond, above 8? Anjana?
I had some calculation problem, I guess, sir. I got something of 7.8 into some factor, which I think is wrong.
Yeah, simply you just see that 1 nanojoule per second and your photon energy is 0.8 times 1.6 into 10 to the minus 19 joule, right? So 1 over 0.8 into 1.6 10 to the minus 19 joule, you can get number of photons, and that's supposed to be, you are getting 7.8 multiplied by 10 to the 9. Per second you will be getting about 7.8. If Murali Krishnan whatever is saying, if that is correct, then per second you will get 7.8 into 10 to the 9 photons crossing, and in 1 nanosecond it will be 7.8, approximately 8 coming, right? Anyone else got 7.8? Can you confirm? Or something else?
Yes, sir, it is coming to 7.8.
7.8, right?
Yeah.
Okay. So who have not, who could not calculate it, maybe it's just a calculation problem, you check it. It is, that's why I have written 8. 7.8, so we know that photon cannot be fraction, right? Just round figure we put 8. Maybe a little bit longer length if you consider, you perfectly supposed to get 8. So now question is that you are getting, if you just somehow expose your photodetector 1 nanosecond, then you can get 8 photons. That means in 30 centimeter, if you consider 30 centimeter, you are getting 8 photons. Another about 30 centimeter, you will be getting another 8 photons. If you consider another 30 centimeter, each time you just chop 30 centimeter, or in the path of laser beam, if you are considering every 30 centimeter, you keep on counting, on an average, you will be getting 8 photons. Now, question is, What is the length? What would be the length for one photon? So about you just divide 30 divided by 8, right? So if you just consider, so about 3.78 or whatever centimeter, about 3.5 centimeter or so, you will be getting one photon. Is that correct? So that means if you have a very weak laser light, then you can actually just think about 1/8 nanosecond time you wait, you will be encountering one photon. Every 1/8 nanosecond, you are supposed to get one photon encountering you, right? If your eye, suppose normally our eyes can sense minimum number of photon, we can realize 4 to 5 photons are there, then we can, if you are in a dark, I think it is coming 4 to 5 photons to you, then you can sense that there is a light somewhere, something you can see at least, feebly or whatever. So you have a photo detector, for example, that can count every photon coming, it can count. So if it exposes for 1/8 nanosecond, then it takes one photon. But problem is that every 1/8 nanosecond you wait, you supposed to get one photon. Then it would be very easy to identify, to separate at least one photon. We know that this duration you're supposed to get definitely one photon within 3.5 seconds. Okay. The problem is it is laser, even though we say monochromatic, very good quality lasers, everything, but it is not like that. It is not emitting photons regularly. That is actually stochastic. Number of photons emits, that actually depends on actually this. I know that every photons it is generating because of the creation operator, a dagger, if you are operating on it, photon number is creating, right? But that operation is not regular. That operation is not controllable to us. It depends on ambience. What we see that 1 nanowatt power, 1 milliwatt power, 1 watt power, that is actually macroscopically you are measuring on an average. But when you go to the photon level, single photon level, one photon by another photon you are considering, that is actually is happening, that is uncontrollable. And that uncontrollability actually happens because of the ground state where no photons was there, that state is counted, some energy is there, that vacuum field. That has also, according to our earlier explanation, that some kind of fluctuations are there, position, momentum, uncertainty is there, h bar over by 2. So position, momentum fluctuation is there. So that actually controls this thing. So that is the reason you will not get a regular interval of every 1/8 nanosecond, you will not be getting one photon for this particular example. Or any other example, if it is one instead of 1 nanowatt, if it is 1 milliwatt, then you should get 8,000 photons. It is not that 8,000 photon, it is coming in a regular way, regularly it is things. So that is actually stochastic. So because of that, we have certain kind of distribution we use to understand that, probabilistic distribution. I will be discussing this in the next class. This discussion from this, I think important, we will be considering about sub-Poissonian light. Okay. So we stop here then.
Sir, could you just elaborate on the first point in the last slide? It's a little confusing. Yeah.
Which one? Actually, this slide, last point, what I said.
No, the previous slide. There were some
slide.
pointers, right?
Okay. This one. Just 1 minute. Is it visible route? No. Yeah.
Yes,
So you see, I have mentioned that laser emission is a certain frequency, monochromatic. That is assumption, though it is not perfectly correct. One particular frequency we can consider that is like a mode, particular k value is there, right? And we have shown that this laser light, monochromatic laser light, if you treat like a electromagnetic wave and introducing vector potential, that can be considered as a harmonic oscillator. And once it is harmonic oscillator, you represent it by vector potential, but I have shown that is equivalent to a harmonic oscillator for a quantum particle of mass m in parabolic potential. So there we used to use certain kind of state function psi. That state function, again, we could consider that state function as a function of xy position. I think ground state we have shown that it is a Gaussian, and we can actually operate a dagger to get a higher excited state. That will be also function of x and so on. But we can show that that can be considered like a mathematical, just kind of complex entity. It can be assigned like a state function psi as a vector. Here also we can consider that a laser mode, laser frequency, that can be considered that can be represented like a state function psi. Okay, it's just kind of quantum mechanically anything, it is very difficult to really visualize, but mathematically we try to visualize. Directly you cannot say that. We can visualize that, okay, there's a state function psi for a laser mode. And that state function, you know, if you operate that particular mode, if you operate, again, we know that the creation operator, annihilation operator works well for the quantum harmonic oscillator. Here also, it should be something like that type of operator should be available. We have to define that. I will explain that later. But for the moment, I'm just relating from there that we should have a creation operator like A dagger and annihilation operator like A. So when you operate on psi, then you mean that you are adding one photon to the laser mode, laser emission. Earlier it was emitting for 100 photons. Now you are operating one things, then it will be emitting 101. Right? The last point says that if we assume that is quantum state with certain kind of description of psi n, meaning there are n photons in that mode. That means I can have a state where no photons are there, and that no photon state is nothing but the ground state, n equal to 0, psi 0. And once it is psi 0, you should have that annihilation operator. If you annihilate that, you should supposed to get 0. That is what we mentioned, we discussed several times for the quantum harmonic oscillator, right? So the psi node exists then, quantum mechanically. Even when there is no photons are there emitting from the laser. That psi node, even your laser is not switched on, that psi node present with energy, specific energy h cut omega by 2, because that is the 0 point energy, that's the solution, mathematical solution, quantum mechanically. And that actually called 0 point energy, and that corresponding to psi node. So even when there is no laser, photons are not there, you have energy there. That energy is called vacuum state energy, psi naught energy, energy corresponding to psi naught. And we know that psi naught also, it is not a well-defined thing. We express like a Gaussian, but if you are just considering where is the quantum particle, what is the position, what is the momentum, that is again delta x, delta p equal to h cut by 2. So that follows the Heisenberg uncertainty condition. So here also you will see that this energy, if it is at all describing some kind of electric field and magnetic field, 0 point energy, that is not also very well defined. How much electric field, how much magnetic field, that is not well defined. So they fluctuate. They somehow uncertain, probabilistic. So that probabilistic nature actually influence how this A dagger A, that means creation operator, photon creation, photon annihilation, becoming like a stochastic. That is the reason in any laser, even if it is well-defined, coherent, perfect, good laser source, you won't get a regular photons, regular photon emission in a regular interval. That's some kind of stochasticity is there. Even though we are operating a continuous pump you are giving to your laser source. That is the point I wanted to mention. Is that clear?
Yes, sir. My doubt was like, how can the wave function just depend on the frequency of the photon? So why it doesn't depend on anything else? So maybe when it proceeds, I might get a better idea.
Okay, probably we can discuss again next class. Maybe some of you are missing. Yeah. Okay.
Okay,
All right.
sir.
Bye.
Thank you, sir.
Thank you.